Okay. So let me start by remind you what we have done last time. Zoom'daki arkadaşlar da beni duyabiliyorlar değil mi? Sanırım duyuyorlar.
Duyuyoruz hocam.
Tamam, tamam, sağ ol. Okay. So last time, for a given curve, beta in R3, we defined the following. Suppose this is unit speed curve, meaning that the derivative of beta, the velocity vector of beta has length 1 for all s. Then we defined Ts to be just beta prime s. And then we took the derivative of this and divided by its length. Of course, we assume that our curve is so that, this is never zero. So it's a regular curve. This means your curve is regular. We assume we have such a curve. Otherwise, we cannot find the normal vector. And this quantity here is called curvature. Kappa S is just the scalar value of the instantaneous change in the velocity vector. And then we defined ds as ts cross product ns. And we know that since this is a unit speed, unit vector field, its derivative is always perpendicular to each other. So if suppose you have a curve like this, if this is ts, the tangent vector, and this is the normal vector, these are perpendicular, and bs is the cross product, so it is also perpendicular to the to both of these. So it should be something like this, bs, so that all these are perpendicular. Okay. And this is a unit vector also, because these are both unit vectors. Therefore, norm of b is equal to norm of t and norm of n, and this is equal to 1 for all s. And then we have the following equations in terms of derivatives. So t prime is just kappa s, n prime s is just kappa s times ns, I am sorry. N prime is just minus k times t s plus tau s times bs, and b prime s is just minus tau s ns. Okay. This is the curvature at beta s, and tau s is the torsion of torsion at beta s. Okay, so that's the summary of what we have done last time. We derived all these equations. Yeah, yeah, yeah. Yeah. Uh, Probably, yeah. In Riemannian geometry, there is so-called curvature tensor. It's also skew symmetric. Probably it is related to that. So it is a net common thing actually in differential geometry. Well, some of them are symmetric, some of them are skew symmetric. Yeah, this one is skew symmetric. Let me write down the matrix. Okay, so T prime, N prime, B prime as a matrix. This is equal to 0, kappa 0, minus kappa 0, tau 0, minus tau 0. And then we have T and B. And you see that this matrix is skew symmetric. Okay. Yeah, I couldn't answer your question, I guess, completely, but it's a general actually theme in differential geometry. Yeah. Uh, I don't know. Well, this thing is called Frenet frame, but I don't know whether this matrix has a name or not. It is, related to curvature, of course. This is already called curvature K. Tau is called torsion, but whole thing is just about second derivative, right? You have your curve, you take derivative twice, so the whole thing is actually a curvature matrix. In higher dimensions, we have curvature form, and it's a two form. And I guess this is something like that. Yeah. Okay. Last time we also defined so-called a plane curve, right? Let me remind you that a curve in R3 that lies in a single plane of R3 is called a plane curve. Okay. So suppose you have some plane in R3 and you have a curve, space curve, but it lies inside this plane. Okay, then we will call it a plane curve because it lies inside the plane. And here is a proposition which characterizes plane curves in terms of curvature and torsion. actually just torsion. Let beta be a unit speed curve as above in R3 with positive curvature. Okay, positive curvature. Then beta is a plane curve if and only if torsion is 0. What we mean by torsion is 0, it is 0 for all s, of course. This means torsion as a function of s is equal to 0 for all s. Okay? Şunu birazcık küçülteyim. Yok, ne yaptım ben? Okay. Now let's switch to the second board. Yeah, it is 1 over the radius. We will see that. No, it is unit speed. You can go around the circle with unit speed, right? Yeah, so. Oh, no. Its torsion is 0, curvature is positive. Yeah, you're right. Here is the proof. Now, first, suppose that beta lies is a plane curve in the plane, say gamma. Bir tane isim verelim. So suppose this is our plane gamma, and our curve lies inside that plane beta. If P is a point in gamma and Q is a normal vector to gamma, then the dot product beta S minus P dot Q is 0 for all S. Why is that? Let me draw another picture here. So this is, let's say, our normal vector, okay, to the plane, okay, Q. And this is any point in the plane, and this is my curve, okay, and this is my beta S. Beta S minus P is this vector, okay. This is a vector in the plane, and Q is a normal vector to the plane. Therefore, it is perpendicular to all the vectors in the plane. Therefore, the dot product of Q with this vector has to be 0, okay? Well, since this is a differential geometry course, what is the next thing we do? We take derivative, right? So let's take the derivative. Take DDS of both sides. If you don't know what to do next, just take the derivative. Okay, so when you take the derivative of this gadget, right, you apply Leibniz rule, derivative of this, which is beta prime dot q plus this gadget times derivative of this, but this is a constant vector, its derivative is 0, and this side is already 0. So the result is this: beta prime minus p derivative dot q plus beta s minus q, no, minus p dot product with the derivative of q, which is 0, and we have this. And what is this? This is just beta prime s minus 0 dot q is equal to 0. So this means what? The velocity vector is always perpendicular to the so beta prime, so ts, which is beta prime s, is perpendicular to the vector q. Well, so this means the velocity vector b prime s, which is ts, is in the plane because it is perpendicular to the normal vector. So beta prime, in other words, beta prime s is in the plane gamma. Of course, this is not surprising. I mean, your whole life is the plane, right? You are in the plane. Therefore, anything related to that thing should lie inside the plane. That's not unusual. Okay, now okay, what is next? Now, n is just derivative of ts divided by kappa s. So this is just what is derivative of this? It is the second derivative of beta kappa s. Okay. Okay. So what is B? B is bir dakika. Şimdi B T cross N değil mi? O zaman şeyi göremiyorum da burada sanırım şey diyeceğim. Beta prime şeyin içinde, plane'in içinde, türevi de plane'in içinde. O bariz mi? Bir dakika. Beta prime s dot q is 0, right? We have this. Okay. Take derivative right, I have this. Take derivative one more time. So dds of beta prime s dot q is equal to 0. If you do this, you will get what? Derivative of this, which is beta double prime dot q plus beta prime s dot q prime, which is 0. So we obtain the following. Then we obtained it. Beta double prime times q is also 0. So this means what? Beta double prime s is also perpendicular to q. Therefore, the vector n, which is just 1 over kappa s times beta double prime, this is perpendicular to q. Therefore, this is also inside the plane. So t is inside the plane, the vector t, right? Ts is inside the plane. And this is inside the plane. So let me show it to, right? Since t is perpendicular to q, t is inside the plane, and n is inside the plane. Therefore, b is perpendicular to the plane. Hence, b, not beta, b, s, which is ts cross product ns, is perpendicular to the plane. Değil mi? If you take two vectors in a plane, and if you take cross product, you get a vector normal to the plane. Therefore, this cross product is normal to the plane. Okay. In other words, Q and B are parallel, right? Q and B are parallel. So maybe I may draw these three vectors like this. So this is T, and it's something like this. And B is this vector. Okay. T cross N is equal to B. And this vector B and Q are parallel to each other. Okay. So and we know what? We also know that, so this is true for all S, of course, right? For all S. S in I. Moreover, BS has length 1. So this vector is parallel to this one, and the length of this is always 1. This means, you know, this vector is just the vector Q, right? Divided by its length. Hence, and thus BS is this vector Q divided by its length, right? Because it is parallel to Q and it has length 1. Therefore, B should be this vector, değil mi? Elinizde bir vektör alanı var. Bu her zaman bir verilen sabit vektöre paralel ve boyu da bir birim. O zaman o vektör bu sabit vektörün kendisi. Bir normalize etmeniz lazım, boyuna bölmeniz lazım birim olması için. Alright. But this is a constant vector then, hence B prime is just 0 because it's a constant vector since it is a constant vector field. But if beta prime is 0, what was beta prime? From our equations, beta prime was minus tau times ns. However, 0 is equal to beta prime s is minus tau s times ns. And this is a non-zero vector field. This vector is never 0. But for this product to be 0, then the coefficient, whatever that is, has to be 0. Okay? And since ns is never 0 because this is a unit vector, we must have tau s is equal to 0 for all s. So this proves one direction, okay? This proves that if your curve is a plane curve, then the curvature, the torsion function has to be identically 0. So this proves one direction. Okay. For the other direction, conversely, assume that tau is 0 for all s. Okay. Now I'll show that we must show what? Must show beta is a plane curve, right? Beta s is a plane curve. Okay. This is what we need to show. How can we do this? Well, if tau is 0, then B prime S, which is just minus tau S times ns, and this is 0, therefore this is 0 for all s. Therefore, this vector field, whatever it is, it's a constant vector field because its derivative is always 0. Hence, Bs is a constant vector field. Say this vector is just Q. Öyle mi yapıyoruz? Evet. For some Q. For S. Bu sabit bir vektör ya. O vektöre Q vektörü diyelim. Şimdi buradaki Q'yu unutun. Hani o resim yok elimizde. Ne var? Bir tane curve var. Bu curve'ün torsionu 0. Ben ne göstereceğim? Bu curve bir tane plane'in içinde yatıyor. O plane'i bulmam lazım. Bulacağım iki şey olmalı. Bir plane'in normali, bir de üzerinde bir nokta. Nokta sorun değil ama normal lazım. Ben de diyeceğim ki işte normal vektörü bu. Tamam mı? Bunu da tabii uydurmuyoruz. Hani buradaki computation bize öyle olduğunu suggest ediyor zaten. Okay. All right, so let's switch to the board one. Let me, okay. Now consider the real valued function f of s, which is beta s minus beta 0 dot product with b for all s. Okay, I define a function. What is this function? I take the point beta s on the curve, subtract this from the initial point of the, not initial necessarily, some point, a fixed point on the curve. Look at this vector and take the dot product with the vector b. B was this constant vector q. It's a constant vector. So, right, this is just actually q. Right? So I don't know whether this curve is a plane curve or not. What I do is this. Here is the point beta 0. Here is the point beta s. I consider this vector and take dot product with this vector q. Q is some vector in R3, any vector, not any vector, of course. It is the vector b. Okay, now what do we do next? Well, we just take the derivative, of course. Then f prime s. What is this? This is just beta prime s minus derivative of this constant vector is 0. Dot product with q plus this plus derivative of q, which is 0. So I have this. But we know that yeah, this is b. This is just t, right? The tangent vector. This is r vector b, and t and b are perpendicular to each other. Therefore, this is just 0 for all s. Right? B prime is the tangent vector to the curve, unit tangent vector. Q is just the vector b, and we know that t and b are perpendicular to each other. Therefore, this dot product is 0. So this means what? This means that this function f of s is a constant function. Okay. Okay. So f prime s is equal to 0 for all s. This means, hence, f of s is a constant function. What is that constant? Well, so f of s is equal to f of 0, right? For all s. Since it is constant, it takes the same value at all points. But what is f of 0? When you plug 0 here, you get beta 0 minus beta 0, which is 0 times q. So this is just beta 0 minus beta 0 times q, but this is the 0 vector, therefore this is 0. So this means f of s is 0 for all s. Okay, f of s is 0 for all s. And this means what? So let's, yeah, write down what we have. We have 0 f of s, and that is just beta s minus beta 0 dot q. So this means if this is the point, let's say, let's give a name to this q. So I have the following. Whatever that curve beta is, there is some point here. Well, actually, it is also on the curve P, which is beta 0. And all these vectors are perpendicular to this. This means that this curve lies inside the plane containing the point Q with normal vector, containing the point P with normal vector Q, right? This means that beta S lies inside the plane passing through the point P, which is beta 0 with normal vector Q. Okay. Değil mi? Bu vektör buna dik. Bu da ne demek? Bu vektör, this vector lies inside a plane. Well, no, this means this vector is always perpendicular to this vector. Therefore, this vector lies inside a plane admitting Q as a normal vector. But this point is fixed, right? Fixed. Therefore, this point should lie inside the plane containing P with normal vector Q. Okay. Sorusu olan var mı? What? Yeah, sure. Yeah. Hence, so this is true for all S, hence beta is a plane curve. So this finishes the proof. Okay. We will come to that. Yeah, it can be like that, right? You may move with non-constant speed on a plane. Yeah, that's possible. We will come to that. It's the next section, actually. But before we pass to that, we will do some more applications. All right, so here is the lemma. If beta is a unit speed curve with constant curvature, kappa, constant and non-zero curvature, and torsion 0, then beta is a part of a circle of radius 1 over kappa. So We have a curve, space curve. The torsion is 0 and the curvature is constant, a positive constant. Then the claim is that that curve is a planar curve since the torsion is 0, but more is true. It's a part of a circle, and the radius of the circle is just 1 over the curvature. Okay, proof is, we will use the previous work. Now, this is 0 implies, so tau of S is equal to 0 for all S, implies that beta S is a plane curve. Plane curve. Consider the curve. So our curve lies inside the plane. We know that, okay? Our curve is inside the plane. We know that. Consider the curve, this one, gamma S, which is beta S plus 1 over kappa times n. N is the normal okay. I had this curve beta. I consider another curve. I add to beta 1 over kappa. This is a number times ns. Ns is the normal vector of the curve beta. Okay. Now, then by the assumption, and Frenet formulas, what is the assumption? Assumption is that this is a constant function, right? Curvature is constant. We have this gamma prime s. So this is just d gamma ds, right? We just take derivative. What is this? This is just beta prime s plus, this is just a constant by the assumption, times n prime s. But what is n prime s? Well, beta prime s is the tangent vector plus 1 over kappa. N prime s is just, by the Frenet formulas, minus kappa times t. So ts, of course. Well, kappa is non-negative, I mean non-zero, so these are cancelled. I have minus t plus t, so this is just 0 for all s. This means what? This function is constant. It's a vector valued function, but it is constant. So this means is equal to let's say some constant for all s for some constant c. This is of course a point actually in the space, right? It's a vector valued function, so It's a constant vector. But this means what was gamma? Gamma was this. So this thing is equal to C, right? So we have this. For all S. Okay. Well, then I can do this. Beta S minus C is equal to minus 1 over kappa times NS, right? I just took this to the other side and this one to the others to this side. This is a vector, this is another vector, and this is also a vector. I may regard this vector as a point actually in R3. So what we have is then following. Okay, let me see what we have. So inside this plane, I have a fixed point. And beta is somewhere here. And this distance, so this vector is minus 1 over k times this. Okay. Now, if I take norm of both sides, this is just 1 over kappa, and this is a norm, this is a unit vector, therefore this is equal to 1. This means what? My curve lies inside this plane gamma, and the distance of this point to this fixed point is always 1 over kappa. This means that this point is on the circle in gamma with center C and radius 1 over kappa, right? This is true for all S. So this point lies in the plane, in some plane. Here, gamma is the plane. Zaten onu biliyorum. Gamma plane'inin ne olduğunu biliyoruz. Tamam, özür dilerim. Ona gerek yok. Evet. Neyin sürekli olması? Beta connected şeyse, continuous, o zaman bu da interval olduğuna göre tek parça olması lazım. But it doesn't have to be, well, but it's a unit speed curve. It moves on the circle with unit speed, right? Its speed is constant. Therefore, it should move on the circle with unit speed. It cannot stop or go backwards. Okay, by assumption, it's unit speed, therefore it just go about the circle, but it doesn't have to be the whole circle because I don't know how big this interval. So it might be a part of the circle, right? This interval could be something very small. So it could be just this part of the circle. Tamam mı? But it cannot stop or go backwards, or it cannot do, zigzag. Yani ileri geri gidemez. Hızı sabit çünkü. Hep bir. Zamanım var mı? Kalmamış. Okay, let's stop now.